Okie dokie, folks. Welcome to Chapter 4, Section 4.1. So we're going to start off by looking at what's called the extreme value theorem, which we'll abbreviate EVT. This says if f is continuous on a closed interval from a to b, so we're talking about x values here from a to b, including a and b, then f has both a maximum value and a minimum value on that interval. Sounds pretty obvious, right? Let's look at a few quick examples. Alright, so here we have 4 quick sketches of a function. Our first one here, we would have our maximum value on the interior of the function, and our minimum would also be on the interior somewhere. So the extreme value theorem is just talking about how this continuous function is guaranteed to have a max and a min. The next one here, our max and our min occur on the endpoints of that continuous function. Here's an example where the minimum occurs on an endpoint, but the maximum happens somewhere on the interior. And our last one here, we can see our minimum is on the interior and our maximum occurs at an endpoint. So you could have any combination of the min and the max occurring on the inside or on the endpoints. Okay? So again, to summarize, extreme values can occur at the endpoints or on the interior of a function. So just jot that down. Alright, so we can take this a step further and we can classify our extreme values. So take a moment and sketch this graph, which is what we're calling f. Okay, first, if we were to look at the absolute lowest point and the absolute highest point, we can classify these as, go figure, an absolute min or an absolute max. Alright, it is the absolute lowest and the absolute highest points that we see. Sometimes we call them a global min or a global max, but usually they're referred to as absolute min and max values. Okay? Now, don't be confused by the fact that this absolute max occurs at a sharp turn. Yes, it's true its derivative doesn't exist there, but it could still be the absolute highest point on our function. Now, these other points we refer to as a relative or a local min or max. So, in other words, if we were to focus in on this general neighborhood, all right, that general area of the function, okay, if we were to look pretty close at this region here around these points, we would see that first up here within this region, that is a high point, right? So relative to that general area, or within that local area, we have a max. Likewise down here, within this relative area or this local area, we have a min. And then over here, since the function is decreasing, this is the lowest point within that little neighborhood. Now, if we go back to our absolute min and max points, it is also true that those are relative min and relative max points, right? Within this little neighborhood, that is a relative min, and within this little neighborhood, that is a relative max. But the better way to classify it is to say that they are absolute min or absolute max points. All right. So we technically have all of these points represented as relative or local min and max values. But again, the fact that these are absolute min and max values, that kind of trumps it as we classify them. Okay, so let's take it a step further and look at a very important definition of a term called a critical point. This is a term that you'll see over and over again in this course. So, any point that is in the interior of the domain of a function, so any point within the inside of our function where the derivative is either equal to 0 or the derivative does not exist, is known as a critical point. So notice up here we have a situation where our derivative is equal to 0 because we have a horizontal tangent line. Same thing down here our derivative is equal to 0. Okay, so these are both critical points, right? I'll abbreviate CP for that. And this value over here, like I mentioned earlier, the derivative does not exist because it's a sharp turn. So this is also known as a critical point. Okay, so we have 3 critical points on this particular function. All right, we're not looking at the endpoints. We're looking at strictly inside the function, all right, inside its domain. So points where the derivative is either 0 or does not exist. Those are known as critical points. Okay, let's look at an example. Suppose we want to find the absolute min and max values of this function f of x equals x raised to the 2/3 on the interval from -2 to 3, including -2 and 3. Keep in mind this interval represents x values. Alright, so anytime you're asked to find an absolute min and max, what you want to do is you want to create a table. And this table is where we are going to track what the y value is for different x values. We're ultimately trying to find the biggest y value and the smallest y value. So we know that our absolute min and max values can possibly occur at the endpoints. So let's plug in these values into the function. Okay, so sometimes you're not allowed to use a calculator, so you have to go as far as you possibly can. Now -2 raised to the 2/3, well, the numerator means that's the power, so -2 squared would be 4, and then you're left with raised to the 1/3, okay, which is really the cube root of 4. And likewise down here, you would have 9 raised to the 1/3, all right, and then this is the cube root of 9. So we don't know exactly what those numbers are, but we know which one is bigger. Okay, we know the cube root of 9 is going to be bigger than the cube root of 4. Now, if we went to a calculator, you would see that this is approximately 1.6, and this is approximately 2.1. Okay, so keep that in mind. All right, so we know the other possibility for an absolute min or max could be critical points, right? So those points within the interior of our function. So remember, critical points are points where the derivative equals 0 or the derivative is undefined. So of course we need to first find our derivative. So go ahead and do that. So when we find our derivative using the power rule, we get 2/3 x to the -1/3, and this can be rewritten as 2 all over 3x to the +1/3. So you generally want to get rid of your negative powers. Okay, so now we're looking for where our derivative is equal to 0, and we're also looking for where our derivative does not exist. Okay, well, to find where it's equal to 0, you're going to set that derivative equal to 0, and in this case we're going to cross multiply and try to solve for x. Well, notice you get 2 equals 0, which we know is not true. So that tells us that we don't have any critical points where the derivative is equal to 0. Okay? Now, the derivative being undefined. Well, this is a rational function, and we know we can't divide by 0. So if x were 0, that entire denominator would be 0, and therefore the derivative would not exist. So x equals 0 is a critical point. So what that means is it's a possible candidate for an absolute min or an absolute max. So if we put 0 into our function f of x, all right, we have 0 raised to the 2/3. That's just 0. So now it's a matter of comparing our values here and picking out the one that is the highest and picking out the one that is the lowest. So if we summarize here, we can say that our absolute max is the cube root of 9, and this happens when x is -2. And sorry, it should be when x is 3, not -2. Okay, if we look at our table here, when x is 3, all right, we have our highest y value, and we're going to have our absolute minimum, at 0, and that happens when x is 0. Okay, so keep in mind too that we have to pay attention to our interval. So it's possible that you can get a critical point, but it might be outside of that interval. If that's the case, we're going to reject it. All right, so 0 is definitely somewhere between -2 and 3, so that is a possible candidate. Okay? Okay, last example, same thing. We want to find the absolute min or max. This time our function is y equals e raised to the 2x, and we're looking to do this over the interval from 1 to 4, including those values. So again, the first thing you should do is establish a table where we are tracking the different y values for various x values. So we know that the endpoints are certainly candidates for the absolute highest and the absolute lowest points. So let's drop those into the function for x. All right, our first one is e squared, and our second one would be e to the 8th. We know e to the 8th is bigger than e squared. Okay, next, let's check for critical points. So we need our derivative. So our derivative is pretty easy to find. Remember, e for easy. It's easy because you get the same exact thing back. But don't forget, we need to chain along the derivative of the inside, which would be 2. So our derivative ends up being 2e to the 2x. So let's look for critical points. All right, so we're going to first take our derivative, and we're going to set it equal to 0, and we're going to try to solve for x. Well, I can divide this 2 over, so I have e to the 2x equals 0. Now recall, to undo an e, we're going to take the natural log of each side. Well, notice that when you do that, we have the natural log of 0, which is not defined, right? So that doesn't exist, all right? So this means that we don't have any points where the derivative is equal to 0, okay? So the other thing to check for is to see if the derivative is undefined. Well, this function, 2e to the 2x, we know it's an exponential function, okay? And exponential functions are never going to be undefined. All right, those are smooth, continuous curves. We aren't going to have any spots where it's undefined. In other words, you can put in anything for x here and always get something out for y. So what this means, so let's just jot down here that there's no points where f prime equals 0 or where f prime does not exist. Okay, therefore, right, 3 dots for therefore, there are no critical points. So what that means is that we have no additional value to add to our table. So that tells us that this e squared is our absolute min, and this e to the 8th would have to be our absolute max. So sometimes in these problems, you're not going to have critical points, right? You're not guaranteed to have a point on a function where the derivative is equal to 0 or is undefined, okay?